Hello, good morning, everyone, and welcome to this parallel session on hydrogen storage and distribution. My name is Dionisis Tsimis, and I'm a project officer for the Clean Hydrogen Partnership. I'm joined today by 5 speakers that will be presenting their projects. We have a very nice panel put together, a very interesting set of projects. We'll be starting with above ground storage, going a bit in the underground storage part, and then looking at hydrogen distribution, while concluding with a bit more underground storage for you. I would like to encourage you all to please post your questions on Slido. Make sure that you have selected the right session on the right, and to try to make this interactive, this session as interactive as possible. And we will be answering all your questions at the end of all 5 sessions. Thank you very much for joining us, and I give the floor to the first speaker, which is Professor Marcello Baricco from University of Turin, which will be presenting Project HyCARE on above ground storage using metal hydrates. Marcello, the floor is yours.
Thank you very much, Dionysus, for the introduction. It's a pleasure for me to present the HyCARE hydrogen carrier for renewable energy storage to this meeting. HyCARE is a project that was answering to the call of 2018, and actually it was starting at the beginning of 2019, but because of COVID, it was a bit extended, and it finished just the last July. Here you can see a map of the partners of this project. We have 2 big companies. We have different research centers spread around Europe. The main goal of the project are here represented, and I suggest you to concentrate on the blue words. The idea is to have a demonstration of storage of about 50 kilos of hydrogen, but the main goal was to play at low pressure and at low temperature, so close to the normal conditions. Another goal was to have a low footprint for hydrogen storage, and this has been reached with the innovative design. And the use of metal hydride was the core of the project. But the innovation, the main innovation, is to join the metal hydride with the heat storage obtained by the phase change material. And the project was aiming to integrate the storage system together with an electrolyzer and a fuel cell, and to be demonstrated in a real applications. Of course, as usual, we need to provide a techno-economical evaluation and life cycle analysis, and then to try and to find suitable applications. But let me spend 2 words about the innovation of HyCARE. When you put hydrogen into the metal hydride, you produce heat. Usually this heat is just it just disperses, it just put away. But in this project, it has been saved in a phase change material. So when you need hydrogen back, you have heat already available in your system because the phase change material is producing heat for you, and then you have hydrogen out. And the main goal of this approach was to improve the efficiency of the whole system, maintaining the pressure quite low, below 30 bar. So this was the idea. So the first step was basically to define the metal hydride. You know that the metal hydride can be described with the PCI curves that are obtained in isothermal condition. You can see them in the screen. But in this case, we have an input pressure of 30 bar and an output pressure of 1 bar. 30 is the pressure of the electrolyzer, 1 is the pressure of the fuel cell. So the yellow square is explaining what is the pressure range that we are using in our application. This pressure range, because of the material that has been selected, was together with about 1 weight %. that is quite low for mobile application, but it's quite interesting for stationary application because the volume is quite limited. So we reached the definition of the alloys, and then we moved to the industrial production. So about 4 tons of this material has been produced. They have been collected in pellets. So there has been a polymer that was sticking the different powder, and this powder has been inserted inside of the tanks. You can see on the screen the tanks that was able to get about 46 kilos of hydrogen, all them together. But in order to obtain the innovative design, we needed to join it with the phase change material. The phase change material has been inserted in suitable tanks that was connected with the hydrogen tanks through a suitable fluid. Thanks to this phase change material addition, the efficiency of the whole system was quite high, about 90%. So there were basically no need of external sources to store about 50 kilos of hydrogen. This was the main achievement of the project, and we are quite proud to show the picture of the final system. You can see on the left the final system. In the top, you can see the hydrogen tanks. In the bottom, you can see the phase change material tanks. It is clear that the addition of phase change material that is very useful from the point of view of efficiency is not very good from the point of view of the volume, because the phase change material is using a significant volume. But the idea of the project was to demonstrate the suitability of this approach. Different possible design can, of course, improve significantly the volume effect and the footprint in order to optimize the system. On the right, you can see the group that was showing the system working in April this year in Paris in the very final event. As usual, we were supposed to exploit the system to find if there were any exploitation, and thanks to the Horizon Results Booster, we were following this different approach, and we basically have in mind to see how the system can be inserted in the real market. In the middle, you can see the result of the life cycle assessment. It's clear that the system, because of the use of hydride, can have an impact. But if you have a suitable defining of the material and how fast you substitute the metal hydride, the impact in the environmental impact can be significantly reduced. On the right, you can have a look at what is the, let's say, economical impact. That is a sort of the cost of the system, and it's clear that it is not comparable with a simple storage of the hydrogen at 30 bar. That is, of course, the cheapest way, but using the metal hydride, you can have, at the end of the day, costs that are comparable with a compressed gas and even cheaper than the liquid hydrogen. So the results basically show that there is an affordable way to obtain and to apply this approach. As usual, we were engaged in the communication and dissemination activities. I'm quite proud to say that 2 of our young students got the award from Hydrogen Europe Research, so we are very proud of that. And we were also joining TV programs and something like that. But let me just to conclude and leave you for 3 minutes video that is showing the system working in the real life. Thank you very much, Dionisis, and thank you to everybody for listening to that. Please, for the video.
Okay, so Marcello, after these years of work, what do you think of the results achieved right now?
We are very excited. We are at the end. The system is here. HyCARE is growing. HyCARE is at the end of its whole activity. Let me say that first, we have our university that was coordinating. Very excited to do that. Second, we have 2 big factories. GKN that produced the pellets, LNG that hosted all the system. We have 2 small medium enterprises. Stu that built up the system, and Technodelta that provided the PCM. And then we have a huge amount of science behind the project. We have
IFE in Norway that provided a lot of characterization. We have INERIS here in Paris, nearby. Then we have EBK that contributed significantly to the wall system. We have Herion that was behind the wall system, and we have EnviPark that was helping us in several matters. So let me say that the consortium was very great, and this is the results of our experience.
Thank you very much, Marcello, for the excellent presentation and the nice video. I very much appreciate your enthusiasm, and yeah, it's very nice to see throughout all the research projects that we had on this topic on metal hydrates, finally to have a solution that is demonstrated at such a scale, and looking forward to see the next steps in this journey. So with this, I think we can move on to the next speaker, which is Arnaud Reveillere from Geostock.
Good morning.
Yeah, welcome Arnaud, and you will be presenting to us your project HyStorIES, where you've done a lot of work. I presented some of your work yesterday, but it's very difficult to capture all the elements. So looking forward to hear from you more details.
Thank you, Dionisis, for your introduction and for the invitation to this webinar. I will present you HyStorIES. It stands for Hydrogen Storage in European Subsurface. It is a project that answered the 2020 call for proposals entitled Underground Storage of Renewable Hydrogen in Depleted Gas Fields and Other Geological Stores. It's not the only project that was awarded. The project that will be presented by Remco, HyUsPRe, was also awarded from the same call. HyStorIES is finished. It has lasted 2.5 years. It finished at the end of June this year, and it has received 2.5 million euro from Hydrogen Europe, from the Clean Hydrogen Partnership, a grant. And also we received a financial contribution of 45,000 euros from our advisory board. HyStorIES is made of 7 partners. It's coordinated by Geostock, an engineering company of underground storage in France. It involves also MicroPro, LBST, Meripass from Poland, FHA from Germany, Montan Universität from Austria, and CO2 GeoNet, which is an association that by itself includes 17 third parties, geological surveys or research institutes from 17 European countries. So you see the map here. We are really a pan-European project team with a very large coverage. We are coming from 25 European countries in this project. And this is for the team that is actually producing the work of HyStorIES. And we are advised by a team of 13 members of the mostly coming from the natural gas storage or transportation industry that gather in an advisory board and supported us. So I will quickly summarize the work. It's focused on underground storage, and it's based on two pillars. First one is technology development, because a few months ago, pure hydrogen injection in porous media had never been done, and there are technical maturity questions and technical developments to bring. So I will briefly go through the state of the art and through what HyStorIES brought to these topics. And so this is focused on porous media. And the other leg, as the other pillar of HyStorIES, is a techno-economic maturity of underground hydrogen storage, because it is foreseen to be deployed in a very short time frame. And we need to be sure of the next step, and we need to give elements to decision maker to plan for this deployment. And I will conclude my presentation with the implementation plan and what HyStorIES can bring to this implementation plan. So starting on the technical maturity topics, the first one was the availability, the public availability of a database and a geographic one, so a geographic information system of porous traps in Europe. It did not exist, and for hydrogen, there were public databases mostly built from past projects on CO2 geological storage that were done at the European scale, and that already identify a number of aquifers or depleted fields. But it was not really focused on hydrogen, and we did focus the work on hydrogen, and we do provide, it's online, you've got the URL here on the screen, and we do provide a public GIS of possible traps, either aquifers or depleted fields in Europe that could be candidates for hydrogen storage. This is the first technical development. A second one, and maybe the first application of this previous GIS and database, is to use this information to provide an estimation of the porous storage capacity, the storage capacity of hydrogen in porous media. And this has been done. At the European scale, and it's probably the first estimation that is not only based on the conversion of natural gas existing assets, but that is also looking at new developments of new aquifers or new depleted fields that would be converted into underground hydrogen storage in depleted fields or aquifers. A third technical development we developed is about microbiological risk assessment. It's a very active topic. State of the art is evolving very fast, I think. Hydrogen is actually known to be very reactive, and reactions essentially do not happen under storage condition below 200 degrees C. But we also know they can be triggered, catalyzed by microorganisms that make them happen, and this raises questions of consumption of the stored product and of gas quality and possibly technical questions due to corrosion of related to H2S, for instance. So what HyStorIES did is to review, to try to bring elements to assess the risk. So it gathered samples from 12 underground natural gas storage sites in the idea that these sites could have been selected as hydrogen storages too. And from these samples, the microbiological fauna that was present was characterized, and then it was put in the culture, it was developed, and it was put in contact with hydrogen, with also nutrients, with also cores or rock samples from the reservoir, and under atmospheric and high pressure, and we identify the consumption of hydrogen that took place. And we then work to model that at 0D and also at the reservoir scale. So at the end, we came out with this chart that is a risk assessment chart, depending that is a way to sort out and to assess the risk related to microbiological activity for a reservoir with these four criteria: temperature, salinity, carbon sources, and sulfate. Last technical development we worked on is about material and corrosion. It mostly applies to the well infrastructure in the underground. We focused in the underground. Wells are the main mine-built structure of an underground storage in porous media. And standards do exist. Mostly, they mostly were developed by the API, the American Petroleum Institute for the Oil and Gas Industry, and usually do not cover hydrogen. And hydrogen does raise new questions related to embrittlement of steels. And where it is, there are standards for surface application, but they're not directly applicable to underground conditions. So we kind of face, this industry kind of faces a lack of standards for underground hydrogen wells. And HyStorIES did also a very pragmatic and experimental approach on this topic, testing also 12 steel grades and testing, putting them in contact with different environments, including hydrogen, including wet environments with or without salinity, with or without H2S2, and assess the damages that could affect the mechanical properties of the steel, the hydrogen uptake in the metal, in the steel crystal, and then we assessed how applicable is a given steel grade to hydrogen embrittlement. And we also saw during the process of this project, first industry manufacturers move on the topic quite fast, like Vallourec. And when they moved, they referred to HyStorIES report and results. So we are very happy of the fast dissemination to the industry of this research works. So I'm now moving to the second pillar of HyStorIES, which is techno-economic maturity. So now we involve we consider both salt caverns and porous storage. We thought that we could hardly find a coherent view of the permitting readiness at European scale. So we did a survey at the European scale and assessed the maturity of the regulation for underground hydrogen storage. Also we lacked a reference assessment of the environmental footprint and also of the public perception of underground hydrogen storage. So we produced a reference environmental footprint assessment of a new typical project, and we did a survey. Another topic that we worked on and where we was the assessment of the underground hydrogen storage demand. And for that, LBST built an energy model of the European energy system, and they had the variability on the production side, green hydrogen production. They had variability on the offtake sides, And underground storage was a way to balance this. And they found a cost-optimal solution for the energy system in Europe. And this cost-optimal solution did imply having some underground hydrogen storage. So it's a finding of this kind of approach, and it's a quantitative finding. So so we have a quantitative idea of the future demand of underground hydrogen storage under several assumptions. To fit this kind of model, we also needed to bring in the cost of deploying underground hydrogen storage. So we developed a hydrogen-specific cost model for both salt caverns and porous media that is quite clearly defined with clear boundaries, and that is parametric. So it can be adapted to site specificities and to cycles. So to conclude on the implementation of underground hydrogen storage, it's very similar to natural gas underground storage, but there are some differences in physical and chemical properties. On spatial and time frame, we want to deploy that by 2050. It's in 27 years. That's very short when compared to equivalent deployment of energy infrastructure we've known in Europe. We're talking about an industry that does not really have a business frame that is set yet. And we're talking about a development nowadays of an infrastructure business with a probably higher care for public acceptance of such infrastructures. So our overall idea is that in salt caverns, where there is nearly more than 50 years experience, it is seen as mature, but it does not mean that there is no more technical development. There are, and we are doing still and benefiting from a lot of research developments today. And also maturity is not only technical. The three other points that are not technical here are just as true for salt caverns. And for hydrogen storage deployment in depleted fields or aquifers, we don't see an obvious showstopper. Also, the purity of the gas when withdrawn due to the microbiological activity and the mixing can be a question that has to be assessed. So we called for several actions. I will not detail that here, but you can find that on our website. And what I'm also interested in is how can HyStorIES results can be used? How can it be used for deployment plans? Deployment of hydrogen infrastructure are actually proposed by many today. There is this hydrogen backbone initiative that is pushed by gas TSOs. There is H2 Inframap. There is NSOG, a gas DSO and TSO association that are proposing deployment plans. And how can HyStorIES results be used? First, a big result is, I think, the estimation of the technical capacity for porous media that was not there before. And if we combine that with estimations of the technical potential in salt caverns that was already published, we see that these technical potentials are orders of magnitudes higher than what can be the hydrogen storage demand. So there will be a need for selection of sites, and we don't even have to look at offshore sites. It's not mandatory. So if we need to rank and to select, then it's not easy to do that at the European scale. So we proposed a first approach, quite high-level approach, and we ranked 800 porous media traps. So we worked at European scale. We also ranked 18 bedded salt deposits and salt domes in Europe. And for each of these possible storage locations, we estimated a levelized cost of storage for seasonal storage or for fast cycling, and we gave a technical suitability mark. So that's three big, marks that can be looked at for very high-level assessment of storage options. But storage opportunities are local. And to answer that, we've put these three marks on a GIS, on a map that is available on HyStorIES.eu, and you can visit it and use it. and it's giving you the location of these porous traps, 800 of these 21 bedded salt deposits and salt domes that we consider. Last point, last slide from my side is the dissemination activity. So HyStorIES is finished and has done its final conference before the summer. We had more than 400 people attending, so it's a lot in our niche industry. We were happy by the attention the project had. And yeah, we had also the opportunity to do a lot of presentation in conferences, publish some of the results were published in academic peer-reviewed scientific journals. We had general public interviews. I even was invited to the UK's House of Lords to give an opinion on underground hydrogen storage and could talk about HyStorIES. So the project had quite a large reach. Please put your questions on Slido, and I'd be happy to discuss that and answer that. Thank you.
Thank you very much, Arnaud, for this excellent presentation. It's really impressive, the amount of work that you have produced from this project, and it's clear that you're preparing the ground for the future of underground storage in Europe in depleted gas fields. But you were not alone. You had your sibling project as well, and we'll be hearing from HyUsPRe, your sibling project now. And therefore, I invite Remco Groenenberg to talk to us a bit about the results that came from your project and how you are. I think you're also very complementary to what has been done in HyStorIES. So, Remco, the floor is yours.
Thank you, Dionysos. Let me share my screen momentarily. See if I can do that easily. I think I'm sharing already. Now I need to still find you. Okay, so yeah, thank you for these introductory words, and also thanks to Arnaud for laying the foundation for my presentation, actually, in a way. As the sister project of HyUsPRe. So HyUsPRe stands for Hydrogen Underground Storage in Porous Reservoirs. It's an acronym. I'm the lead scientist of that project, and I'm forming a team with my colleague Holger Kramer, who together with we coordinate this project. Yeah, so a project overview. Yeah, we started about 1 year later than HyStorIES, in fact, on 1 October 22, and then we also aim to end about 1 year later at 30 June 2024. That's next year. Yeah, we are still in full flight with this project, about 75% through. Also, looking at project budget, we asked for a contribution from the Clean Hydrogen Partnership with the amount stated, and have further in-kind contribution, also as stated from 10 industry partners that are shown on the right. On the right, you see the consortium partners logos. At the top, you have 7 logos of the executive partners where TNO coordinates, and then there are 3 research institutes and 3 universities involved. So the research institutes are Forschungszentrum Jülich, Energy Institute Linz, and Fondazione Bruno Kessler from respectively Germany, Austria, and Italy. And then the universities are the University of Edinburgh from Scotland, Wageningen University and Research from the Netherlands, and Clausthal, TU Clausthal from Germany. And then we have indeed 10 industry partners that represent industry, the gas storage industry, so to say, as well as oil and gas exploration and production industry, having assets, reservoirs that might be reused for the purpose of hydrogen storage. And we have a TSO in the form of SNAM, a transmission system operator, that is also a partner. So the project summary, so what are its main objectives? So firstly, to assess the technical feasibility, risk and potential of large-scale underground hydrogen storage in porous reservoirs in Europe specifically. So this project focuses specifically on reservoirs and less so on salt cavern storage. Basically, this is a research innovation action. This project, storage in salt caverns, is somewhat higher maturity level. Technological readiness is somewhat higher than storage in reservoirs. Hence, we thought it would be good to focus this project on storage in reservoirs specifically, on de-risking, for instance, geochemical, geomechanical, microbiological flow and transfer processes. Also understanding or having a more accurate cost estimates and identifying business cases for underground storage in reservoirs to play its role in the future energy system in Europe. And also investigating suitable stores and quantifying their storage potential. Also, Arnaud already mentioned this also in his talk. We have focused more specifically on understanding better and quantifying the potential for storage in existing natural gas storage in Europe. Second objective is developing a roadmap for deployment of underground hydrogen storage up to 2050. So also looking at proximity of storage reservoirs to renewable energy infrastructure, evaluating amounts of renewable energy. So what storage capacity would actually be required in the future? What would be the demand for storage? And developing future scenarios and a roadmap for Europe-wide implementation. So our expected impact is what we want to do is to show that underground hydrogen storage has potential, that the risks can be responsibly managed, thereby raising the TRL, the technology readiness level, from 3 to 5, making it ready for piloting, similar to what is already ongoing today with storage in salt caverns. So highlights of project status: 52 deliverables promised, of which 31 have been achieved until now. 3 external webinars we organized, publicly visible. 2 more in one in November, actually this month, and one later this week, in fact, and one in Q1 24. And then 4 e-newsletters. Some consortium meetings were held, and we have our final conference planned for May 2024 in the Netherlands. All deliverables that are public are published on the HyUsPRe website. So I would like to refer the audience to that site, hyuspre.eu. So some highlights of project progress. So firstly, we quantified the hydrogen storage potential of existing gas storage sites in porous reservoirs in Europe, mapped their proximity to areas of supply and demand, and also to connecting infrastructure. And developed a vision on a potential rollout of this infrastructure for storage to meet projected future demand for storage. Secondly, we did quite a few experimental studies. Here I will basically highlight our studies on geochemical and microbiological reactions with hydrogen under geological storage conditions, basically aiming to improve our understanding of how relevant they are for de-risking hydrogen storage in reservoirs. And 30 integrated modeling approach. We developed an integrated modeling approach for performance, integrity, and durability assessment of reservoirs at the reservoir and new wellbore scale, and applied these models in an enhanced form in HyUsPRe in case studies of representative sites. That's what we're doing at the moment. So this is where the contribution, the in-kind contribution of our partners plays a very valuable role in basically having actual physical material of partners' sites, underground gas storage sites, reservoirs available for case study work. So first highlight, European hydrogen storage potential. Here, we basically quantified the storage potential in existing gas storage reservoirs. Came to an amount of 300 to 450 terawatt hours equivalent hydrogen energy. Also found, so what we assume here is that the low-hanging fruit is to develop existing gas storages in Europe, convert them to hydrogen storage, and then based on requirement or additional demand, I would say, and how it needs to be ramped up, look for additional sites in close proximity to the developing network, as much as possible. So indeed, also finding that there is a large potential in gas fields and aquifers in identified storage clusters to develop additional capacity to meet storage needs. So these are then not yet used for storage of gas, but would look to some extent similar to existing sites. And here we proposed a number of templates sites, so notional designs, 2 per cluster. So basically, trying to estimate what the next site would look like when developed in this particular cluster. We published the results of this work in the HyUsPRe Atlas of European Hydrogen Storage Potential in porous reservoirs, and that can be accessed through the HyUsPRe site. Secondly, de-risking geo and biochemical reactions with hydrogen. So we published a literature review on the window of viability of microbial metabolisms relevant for hydrogen storage. So there are microbes living in the subsurface that consume hydrogen for their metabolism to live, and they basically produce byproducts that might pose a risk to materials, for instance, and also to health, safety, and environment. So here what we found is that basically summarizing the existing literature, which is a very active field, this temperature and salinity here are very constraining factors for these microbes. So basically finding that up to about 80 degrees and a salinity up to 2-3 molar of sodium chloride. These microbes, different types of microbes and communities can live in the subsurface and be influential in risks associated with hydrogen storage. So also we are doing experiments on samples of partner sites. We have been doing this at low pressure and are still doing this at high pressure at relevant storage conditions. And there we find so far that, for instance, for sulfate reducers in particular, we find basically the window of viability of sulfate reducers that was known to be a bit extended towards 65 degrees rather than 50 degrees. And 2 molar sodium chloride. So this is still in progress, this work, trying to better constrain at which conditions these microbes are active. Furthermore, on the geochemistry side, so geochemical reactions of hydrogen with rocks and fluids, focusing in particular on a reaction with pyrite in this case, which is present in some reservoirs used for hydrogen for gas storage now. And also in many gas fields from which natural gas is produced in certain areas in Europe. We find that pressure, temperature, pH, and grain size influence the reactivity, and this to greater or lesser extent, this reaction produces H2S. We find in experiments certainly at 120 degrees and higher. We did not find any H2S measured at 40 degrees. So in between, we try to find where at which temperatures this plays a role, and also at what pressures, and also how much hydrogen sulfide gas is then produced, with the ultimate aim to be able to improve models for site-specific studies to de-risk use of sites for hydrogen storage. So we published a database also on mineral reaction rates with hydrogen. This is a collaboration between TNO and Edinburgh, in fact, whereas the previous work was more on a collaboration between TNO, Edinburgh, and also Jülich. So thirdly, modeling case studies and guidelines. As I mentioned, developing an integrated modeling approach, implement and test open source reservoir simulator Dumux. This is a software that can be used for bioreactive transport modeling. We enhanced it for that purpose. Also to be able to apply this software and selected other simulators, commercial simulators that are available from oil and gas perspective in case studies of 3 partner sites. And on the right here on the map, if you look at Europe, and we divided that into let's say 4 regions: Northwest, South, Central, and Eastern Europe. We have partner sites from case studies for partner sites from 3 out of 4, Northwest, South, and East. Central Europe, we have also a site for validation of the model. Ultimately, what we want to do with the results of these case studies is to formulate a set of guidelines for decision making and assessment of reservoir and site suitability. More on the project management level, what kind of risks, challenges, and lessons learned from the project so far. We have a lot of experimental work in laboratories. There is complexity involved in that, and that's easily underestimated. An example is that we had some unforeseen complications with equipment and methods for high pressure, high temperature reactions, experiments involving hydrogen and hydrogen sulfide, which is a hazardous toxic gas at high pH, and this led to some delays. We found mitigations for that, but it takes time. So just to acknowledge that experimental work really also relies a lot on learning by doing and progressive insight. That's a clear learning from our perspective. Also, we had some risk of delay due to dependencies between work streams. And when working particularly with universities, there is the risk of delay in hiring of academic staff by universities that needs to be taken into account. It's common practice that the hiring process starts after the project starts. This takes time and leads to delays early on in the project. On the practical side, maybe a recommendation for projects. It really helps to have a project book with rules, guidelines, and practical information to early on in a project to actually steer everything in the right direction. Exploitation plan and expected impact here on the left. How will the results from HyUsPRe be exploited when final? Well, we have the online HyUsPRe atlas and database of storage sites in Europe. That is basically already available. It visualizes the potential and their performance metrics of these sites, and this can be exploited in site screening studies. We have new experimental data, quite a lot, on reaction of hydrogen with rocks, fluids, and microbes in reservoirs, and also on flow behavior hydrogen under operational storage conditions. This can be exploited by our industry partners, for instance, for improved site-specific modeling. And we developed new algorithms, models, and software code for simulating flow, geochemical, and microbiological processes in reservoirs that can be exploited for de-risking purposes. Also in site-specific studies. So basically looking at increasing the TRL with pilots and demonstration projects and wanting to de-risk that. On the impact side, what we will show and are showing is that underground hydrogen storage has potential, that these potential risks can be responsibly managed, and that basically raising the TRL from 3 to 5 in this project to prepare the deployment of pilots and demonstration sites in Europe. And that we develop a vision and roadmap on realizing this full-scale hydrogen storage in reservoirs in Europe in 2050. This comes back also to Arnaud's last slide, I think, with the maps. There's a lot of development work ongoing. There are visions on how transport infrastructure would develop, and we need to integrate storage into that picture. Based on the project HyUsPRe, but also HyStorIES, of course, and other relevant projects ongoing in Europe at the moment. And then more on the dissemination side, of course, various scientific papers and open access journals. So far 5 or 6, I believe, and still working on increasing that number. I mentioned already the external webinars that we had. We are quite active on LinkedIn, and we'll have a final public event where we will communicate and disseminate the results of the project in its final form. This is what I wanted to share with the audience, and I'm very happy to take any questions in the chat or later in the panel.
Thank you very much, Remco, for this excellent presentation. It's clear, as with HyStorIES, you have produced an incredible amount of results. I really encourage the audience to have a look at your website, where you have everything publicly available, almost everything, especially the atlas. I found it personally very interesting. Same as HyStorIES, these interactive maps are quite fun to play around. So with this, we can, I think, end with the underground scene for now, and move on to above ground again, with moving on to liquid hydrogen, and looking at how we'll probably need to import big quantities of hydrogen in Europe. And Astrinos, you will guide us through how we will import these large quantities in liquid form through shipping hydrogen. So our next speaker is Astrinos Papadakis, who will be presenting LH2 craft. Astrinos, the floor is yours.
Perfect. Thank you very much, Dionisis, for the nice words and the introduction. And I'm really happy having this chance to present our new project compared to the already presented ones to all of you. So I'm here today to present LH2 craft, which deals with the safe and efficient marine transportation of liquid hydrogen. Before moving on to a more structured presentation, I'd like to give a description in a nutshell, because I will not be in the position to present technical details since we are currently performing our baby steps of our project. So I'll try to quickly explain what it deals with. You can see a vessel and you can see a huge area where hydrogen can be stored. So our project combines the need to transport in long distances liquefied hydrogen with the use of vessels, and design the storage of that, the storage facilities of hydrogen, aiming to achieve really large capacities under very extreme conditions of significantly low temperatures. So the combination of these two really immature technologies in terms of liquid hydrogen make the need for LH2 craft to develop and progress. As I said, we are in a very early stage of our project, currently in our 6th month of a 4-year full duration. Our project replies to the call of 2022 for the development of large-scale liquefied hydrogen containment for shipping. And as you can see, I can only claim that we have completed almost 5% of our expected development so far. A few words about our budget and funding. The total project budget is almost 7.6 million euros, with the Clean Hydrogen JU granting more than 5.6 million. Important item here is that we also have 2 additional financial contributions, with the one being the common one by the UKRI for our 2 UK partners. But apart from that, a very significant item is the fact that we have on board our consortium KSOE, actually Hyundai Heavy Industries from South Korea, that bring their own funding of 1.2 million euro. A few words about our consortium. You can see the European map consisting of 13 partners, and also South Korea at the top right-hand side of your screen. Apart from Hydrus, located in Greece, which is the leading engineering and design partner of our consortium, we have on board 4 universities: the National Technical University of Athens and University of Patras from Greece, University of Strathclyde from Glasgow, Scotland, and Technical University of Dresden in Germany. Very important, the fact that we have 3 Ajax major classification societies, namely ABS, RINA, and Bureau Veritas. We have 3 research institutes and associations, EASN, the GEMT, and the TWI, and directly connected to industry partners. I mentioned KSOE from South Korea, the designers of the system that will be described in the following slides, and Gabadi from Spain, the manufacturer now in the LNG industry and in the following years in the liquefied hydrogen industry, and Actemium in France that is performing the quality assessment and integrity of the systems that will be developed. So the project summary, I'll try to explain shortly what we are dealing with. LH2 craft aims at developing the next generation of commercially attractive and sustainable and at the same time, long-term and long-distance storage of large amounts of liquid hydrogen for ocean-going vessels, commercial ones. The project focuses on developing an innovative and totally new containment system of membrane-type tanks for large capacity storage of approximately 200,000 cubic meters, equivalent to the ones already applicable in the LNG storage and transportation sector. Most difficult thing at a temperature of minus 253 degrees, the temperature at which hydrogen can be transported as liquid. At the same time, we'll demonstrate and validate all of our designs in a smaller, of course, prototype of approximately 180 cubic meters. The cargo containment system, that's the tanks, will achieve within the project an approval in principle and also general approval, meaning conceptual design approval and detailed design approval from ABS, one of the major classification societies. And approval in principle will be also issued for the concept design of all the auxiliary subsystems, which consist of handling, distribution, monitoring, and safety subsystems necessary for this technology to be integrated on board ships. And since I mentioned ships, the tank cannot stand alone. It needs to be integrated on board a vessel so that it is carried through our oceans. Thus, LH2 Craft will also develop a preliminary integrated liquefied hydrogen carrier ship design. And at the same time, on desktop study level, we will also examine alternative designs of cargo containment systems and different combinations with other sizes or types of vessels that will carry it. The work breakdown structure of our project, the way forward. Actually, we have split the work in 4 pillars: impact, design and engineering, demonstration, and sustainability and scalability. So in the first part, impact, of course, we have the well-known work packages of the project management and dissemination, communication, exploitation. And apart from that, the intro to the technical work, the implementation plan and the definition of the evaluation criteria for what is needed to be developed. Then pure design and engineering concerning the containment system. Our work package 3 deals with the design of the tank per se. Work package 5 deals with the design of all the auxiliaries and the subsystems, and both of them, of course, throughout the lifetime of the project under the umbrella of detailed safety and risk assessment. Speaking about demonstration, we have a detailed testing methodology and procedure that will be followed, and we're also examining detailed subsystems testing, so smaller tanks being manufactured and demonstrated either in subsystems level or just scaled down level. Of course, the major outcome, the assembly, manufacturing, demonstration, and functionality testing of the prototype. And as we said before, the approval in principle and general approval of both the above by one of the classification societies. Last but not least, the sustainability and scalability will be examined firstly with the ship design and all the alternative scenarios that will assess this scale up, scale down need. And of course, the techno-economical assessment through our work package 10. Now, the only technical details that I could provide for the time being, the first tangible outcomes that we opt for, I can describe the 3 of them that are easily quantifiable and are directly extracted by the clean hydrogen HyUsPRe. Firstly, speaking about the capacity, what can be achieved, what can be designed and in the following years achieved and built. As we speak, there is only one vessel sailing out there, and it holds one tank able to accommodate 10 tons of hydrogen, equivalent almost to 1,250 cubic meters. At the end of the project, by designing the vessel and the detailed cargo containment system, we will have achieved to reach the quantities currently being transferred as LNG, meaning in the LNG industry. and that means 160,000 to 200,000 cubic meters of liquid hydrogen being transported. Second important parameter, the CapEx. For the time being, it's a bit gray zone because we speak about really innovative materials, really innovative designs and technologies. But what we know is that by targeting for efficient integration of materials, combinations of materials, and at the same time achieving economies of scale, at the end of our project, our goal is to achieve less than 10 euros per kilogram being transported as CapEx. Last but not least, the most technical item, the well-known boil-off gas rate. As some of you may already know, while a liquefied hydrogen under these cryogenic conditions is being transported, it regularly loses a percentage of it since it is it creates gases and it vaporizes. So it is a fact. We deal with that. We cannot avoid it. We just need to improve it. The SRIA, the clean hydrogen JU SRIA opts for lower than 0.3, but thankfully our current pre-feasibility assessments and current developments show that we may also achieve 0.2% of cargo loss on a daily basis, a significant improvement on the existing conditions that are applicable. A few words about the risks and challenges. Again, I will try to focus only to the most technical ones. We all understand that the material properties under these cryogenic conditions and also phenomena like the hydrogen embrittlement of all the components that will play a major role in this containment are a critical item that needs to be very, very carefully assessed. In this respect, we have developed a very detailed testing procedure starting from specimens, moving onwards to smaller scale, but at the same time, full scale of composition of the insulation and also the prototype, all of them conducting a detailed testing procedure, examining all the different properties that need to be very carefully assessed. Second important item that is in detail being taken into account, the integration on board the ship. It can imply difficulties and significantly affect the structural integrity of the ship because, as you understand, we speak about huge amounts, huge weight, and very significant impact on the vessel structure. So the way forward is to transfer the lessons learned from the already mature LNG carriers design industry to our new technologies. Same way to mitigate the possible impact of the risk is to deal with the boil-off gas rate, as I explained before. So, of course, there is a chance to face difficulties in attaining the targeted boil-off gas rates. Thus, we transfer the lessons learned from the LNG industry. We do preliminary assessments from a very early stage and have the chance throughout the 48 months to do any corrective actions, improve our testing, improve our simulation, and at the end of the day, improve our design. Now, a few words about the exploitation. I will not speak in detail about all the aspects that can be exploited. I will just try to give you a general idea of what's the chance here. The reason why I'm doing that is to explain what exists out there in terms of LNG industry and transfer it to LH2 industry. Thus, because as we said and we understand, this is our sibling. This is our, this is the basis where we are establishing our new efforts. In terms of LNG, of course, there are several players out there. It is an ongoing and well-developed industry. In Asia, in South Korea, KSOE is already dealing with the design of cargo containment systems and ships that are carrying LNG. And in Europe, Gabadi, our partner, is already manufacturing the tanks that only GTT in Europe can design and build. Not build, design and specify. Always speaking about the membrane type tanks, which is the only way forward for that large amounts. Now, if we speak about liquefied hydrogen, as I said before, only one vessel exists now out there in this sailing. It's called Swiss Frontier, has been built by Kawasaki, and only holds 1.2 thousand cubic meters. At the same time, Kawasaki has already performed significant research and innovation actions, attaining approval in principle for a 160,000 cubic meters design with a different type of tanks. And in Europe, same as in LNG, only GTT is designing in research and innovation level of detail tanks that can host liquefied hydrogen. And that's where LH2 Craft comes to improve Europe's position in this map. It brings the expertise from South Korea, from KSOE, and it combines players like Gabadi with huge experience in LNG, Hydrus, us, that are doing the whole design of the carrier, the ship that is going to hold these tanks, and also 3 IX classification societies that will gain experience and increase their expertise in this new field of liquefied hydrogen transportation. Having said that, a few of the actions and results that are exploitable and are within our target to significantly improve by the end of our project. Firstly, the design of the insulation system for the liquefied hydrogen so that we firstly achieve the minimization of the boil-off. Modular and adaptable cargo containment system design, because we need to make it fit in cargo holds actually of different ships, different sizes. It's not just a plug and play concept that goes together with one type of ship. So we need to be flexible. We need to achieve modularity and scalability. The technology for integrating the proposed cargo containment system into the hull structure is one of the main targets of ours, main outcomes of our project. Of course, with the help of Gabadi, the technology for the manufacturing and erection of the cargo containment system, and last but not least, the design of the ship. These are just a few of the results and the outcomes that will be our core exploitable pool of results at the end of the project, increasing, of course, their up-to-date, very low technology readiness level. Just a few words about our non-engineering actions. We have already established synergies with 2 ongoing projects. One being the NH3 craft. You may identify the common domain because the core team remains the same. It's being coordinated again by Hydrus, and it is 1 year older than LH2 craft. Thus, it can transfer many, many lessons learned from the ammonia storage side point of view, but being both new alternative sustainable fuels, we have a lot to learn in terms of the risk assessment strategies being followed for innovative solutions, safety-related developments, and the regulatory aspects. At the same time, another project named SHIPS, dealing with the storage of liquid hydrogen, but for really smaller capacities and with the main aim to use it as fuel in specific consumers, already on track to start having common workshops, common meetings, and try to exchange knowledge in terms of the supply chain that we need to take into account, safety aspects, the way that hydrogen can be used as fuel, because we will also examine it to a certain extent, and of course the infrastructure and auxiliaries that are required on board the ship. As you understand, there is not a lot to communicate and disseminate up to now. Nevertheless, we already had a very, very fruitful kickoff meeting in Athens back in summer 23. We have already scheduled our next one early 24 in the beautiful city of Paris in France, hosted by Bureau Veritas. A very important development already confirmed. We have booked a slot for a 2-hour workshop in next year's Posidonia event in Athens, one of the most popular shipping exhibitions worldwide. So it would be really nice to see some of you there and have the chance to discuss about more developments, actual developments of our project. And of course, our online presence and digital presence. We recently released our poster and flyer, which will be available soon, if I'm not mistaken, also in our website, and will start to be distributed. Online presence, of course, our website, lh2craft.eu, you can already find in there some of the first developments and mainly the outline, so as to familiarize yourselves with that. And our very active LinkedIn account and Twitter account. Currently, we launched a LinkedIn campaign with at least one post per week in the beginning, presenting our partners and then explaining the way forward and presenting the first developments. So that was all from me. I will be really happy to listen to your questions, and please stay tuned because the nice work is up there and ready to be developed. Thank you very much.
Thank you very much, Astrinos. We put the spotlight very early on your project, but it's because we have high expectations, and we will expect that you will put us back in the race for this technology because we are falling behind in Europe. So yeah, we can move on to the next and final speaker back in the underground scene. Hippolyte, Djizanne will be presenting Project Hipster, which is our first big demo in underground hydrogen storage for salt caverns. We're very much looking forward to your presentation, Hippolyte. The floor is yours.
Yes, good morning, distinguished guests, fellow research and enthusiasts of sustainable energy solutions. It's a privilege to stand before you during this year's European Hydrogen Research Day. Following the other presentation, I believe that our collective endeavor here marks a pivotal step toward a greener future, one where clean energy is not just a concept, but a practical reality. So I would like to thank Nikos and Dionisis for the opportunity to contribute to this vital dialogue. Let me go to the next slide. So I'm delighted, as I just said, to present to you the Hipster project, a kind of a pioneer initiative that represents our first French demonstrator for green hydrogen storage. I'm Hippolyte Djizanne. I'm a rock mechanic, research scientist, and head of Hipster project at INERIS. Hipster stands at the vanguard of our effort to harness the potential of green hydrogen, a clean and versatile energy carrier. The significance of Hipster goes beyond storage. It's about integrating clean hydrogen into our energy system, ensuring security of supply and supporting the decarbonization of various sectors. So about the few words about the project overview. This project began at the response of the call 2020 under the topic cyclic testing of renewable energy storage in a small salt caverns. Our project timeline spans from January 2021 to January 2024, and we received kind of 80%. We have reached by these days 80% of our plan implementation. This indicates also our commitment to maintaining progress in meeting our milestone on time. The total budget allocated for this project is 15.5 million, with a huge participation of the Clean Hydrogen Partnership, around 5 million euros. You can also have another financial support that have been sourced mainly by HyStorIES. We are proud that we have a great consortium of dedicated partners, and including HyStorIES, INERIS, and other prestigious institutions and companies like Armin, École Polytechnique, ASK in Germany, Innovin, Accelera, Element Energy, Broa Consulting, and Equinor. So here I show the map of the partnership of the project, and we can see that to the north we have Equinor in the Norway, who is a leader in energy solution. Moving across the UK, as you can see, our project units a network of expertise from various countries. In UK, we have Element Energy and Innovin, both which are pioneer or in their respective field. And in Germany, we have an engineering company called ESK. But the central of our effort in France are provided by Armin, École Polytechnique, INERIS, and HyStorIES, who is the head of the project. So a few words on HyStorIES. As you can see, as we delve further in specific of our project, HyStorIES is our project leader, and HyStorIES is also, we have a chance to have HyStorIES, who is also the world-class underground gas storage operator. In France alone, HyStorIES operates 600 wells, amplified with a management of 21 underground gas storage. And at the heart of our project infrastructure in HyStorIES, HyStorIES is kind of a strategic location represented here by the red circle. And I can show you a zoom of this on this situation map that provide an aerial view of the HyStorIES facilities, outline several key areas. And the orange boundary is showing the entire natural gas storage facilities, which is one of the critical infrastructure in the neighborhood of our project. And then we also have two other parts of our project, the planned hydrogen production platform, indicated here in blue, and in the green, the planned hydrogen storage platform. Next slide. In this slide, I would like to show you some overview of our project schedule. We can see in this a Gantt planning with detailed timeline that guides our project from the conception to the completion. Starting of the construction, we can see for the hydrogen production platform, the construction has already started. And at this time, we are commissioning all the equipment to be ready to start the production early in the production of hydrogen early in 2024. What about the underground storage platform? On the underground storage platform, at this time, we are performing the mechanical integrating test. I will give you some insight on this. And this should be followed early next year by the mechanical cycling test that was planned for this project. So what can be the very technical challenge to be addressed in our project? As you all know, there are already in the world some soil caverns that are used to store hydrogen. But our project as a pioneer to use soil cavern as an energy carrier to store hydrogen is to firstly, we are focusing to adapt the equipment for hydrogen compatibility, as you can see. This includes piping, valve, pressure vessels, and the purification process following gas withdrawal, ensuring our equipment is hydrogen ready is very essential for both safety and efficiency. Secondly, we are tackling the challenge to ensuring the tightness, as I just said, by performing several mechanical integrity tests with several medium like nitrogen and hydrogen, and that's following by the high frequency cycling, also called the mechanical cycling test at the hydrogen underground storage. And then we want to study in this project, we are studying in this project the thermodynamic behavior of the hydrogen during storage cycling. Understanding this dynamic is the key to optimize our storage strategy and to ensure that hydrogen's quality and energy efficiency upon withdrawal. So, and the last but not the least, we delve into the interaction within the underground hydrogen storage system. This involves the study of hydrogen dissolution in brine and monitoring the chemical and bacteriological reaction in situ. These factors are crucial for maintaining the purity of hydrogen and preventing any degradation of storage capacity. Also on the dimensioning of the purity unit as a surface facilities. So here we have some pictures of our mechanical integrity test. So in the project, we plan to perform 2 mechanical integrity tests, one with the nitrogen, you can see here, and the second with hydrogen. The primary aim of this test is to verify the tightness and the strength of the wall completion, which include tubing, packers, and casing show. The diagram I just show illustrates 2 sets of tests conducted with those 2 gas medium. These tests are well known by Solcaven operator and are fundamental for ensuring the safety and the functionality of our hydrogen storage solution. Now, after these tests, we also plan to have on the site, on the hydrogen storage platform, some kind of mechanical cycling test. In this mechanical studies, we start by the injection of hydrogen into the salt caverns. As hydrogen is injected, an equivalent volume of brine is withdrawn to maintain the pressure equilibrium. For example, in this figure, we have a substantial volume of hydrogen around 26,000 normal cubic meters injected that displays approximately 230 cubic meters of brine. Moving on the second diagram, we inject a little bit of brine into the salt cavern, which pressurizes the hydrogen that was previously injected. And in the third diagram, in the picture, we represent the end of the cycle where the process is inverse. Finally, at the end of the experimentation, illustrated with the last diagram on the right, we have the withdrawal of hydrogen to vent. This represents the final step in our cycle where the hydrogen is released. So I prepare for you some pictures of the 2 platforms. As you understand, in our project, we have 2 platforms. The first platform is the hydrogen storage platform, where the hydrogen should be stored and where the mainly 2 mechanical integrity tests and mechanical cycle tests should be performed. And the other platform is the hydrogen production platform, where with an electrolysis, we should produce green hydrogen. In this slide, I show some picture of the hydrogen storage platform. You can see the wellhead, the cavern safety skid, the brine and water tanks, the electrical skid, etc. And then on the second slide, I present you some pictures of the hydrogen production platform with a view of our 1 megawatt electrolysis, container purification, etc. Okay, coming to the rock mechanic activity, research activities, we are modeling in this project the very worst case scenario. This involves rapid depressurization, fast cycling, and the possibility of a blowout in a hydrogen storage caverns. So on the right, I highlight some factors, some key factors associated with the storage. We can consider risk like excessive volume loss, severe subsidence, spalling, cracks, loss of tightness, and in the very most extreme case, the generalized collapse. Also, key figure like a minimum and maximum pressure, cyclic load, temperature variation, and pressure variation are all quantifiable metrics that inform our models. They allow us to establish threshold for safe operation and identify early warning sign of potential issue. Lastly, I present a list of the most studied phenomena to ensure or to verify the impact on the integrity of underground hydrogen storage. So in this slide, I am showing you, some picture of the blowout phenomena. At the left, we have a natural gas blowout in the Moss Bluff. It's an example of a real accident that's happened in a facility in Texas. Kind of cautionary example of what we aim to avoid. And below, in the middle here, I show a thermal image capturing the flame with and without a thermal camera, the flame of hydrogen. As there is no carbon in hydrogen, the flame can be very invisible, can not be visible at higher temperature. And in the left of my picture, I'm showing you some result of numerical computation in 3D performed by INERIS team to better understand the impact of a blowout of a salt cavern and to calculate the distance of effect of this incident. So to conclude my presentation, I also plan to present you here some distance of effect, because in the blowout modelization, we used to perform two types of modelization, the underground part of the modelization and the aerial part of the modelization. And for the aerial part of modelization, I focus here only in the explosion, the unconfined vapor explosion, but we can study a lot of phenomena like flash fire, like jet fire, etc. So this slide presents the effect distance of the explosion of or the unconfined vapor explosion. So as you can see in this slide, our effort in communicating and disseminating our finding was specifically recognized by the European Union Innovation Radar. And as you can see, we have also organized 3 conference, workshop, and that not only serve as platform to share our insight, but also as forum to engage with the wider community, resulting in the participating in over 45 conferences. This demonstrates our proactive approach to sharing knowledge and fostering dialogue with the energy sector. In conclusion, we all know that hydrogen has been successfully stored in soil cavern for many years, but only limited information is available on the surface, design, and material selection. The Hipster project aims to firstly test or manufacture equipment inside the soil cavern, prove that test procedure and measure leaks, thickness of completion equipment, understand the impact of pressure cycling on the soil cavern, and establish whether there is any chemical reaction or bacterial growth in the soil cavern. Initial results should be available on the second half of 2024 on our website. Thank you so much for your attention.
Thank you very much, Hippolyte, for this very detailed presentation. Good to see your progress, and we're eagerly awaiting your results in the 2024. So I think we're just in time finished. We have a few questions online which I would like to take, but maybe we can go in the reverse order and start with a quick question for Hippolyte. Since you were the last to present, I will start with you. I saw that you are going to be cycling the pressure with brine. You will be injecting brine to increase the pressure, etc. Do you have plans in after the project ends to also cycle fully with hydrogen, or you don't expect that this will provide additional learnings?
No, for the moment, it's not planned to cycle only with hydrogen.
Okay.
We decide to use the balance technique that use brine and hydrogen to mobilize, as it is only a demonstrator, it's TRL5 demonstrator, to mobilize a reasonable quantity of hydrogen.
Understood. Thanks. Thank you for this. And we have a question from online from our guests. Question for HyCARE. How was the system integrated with the electrolyzer and fuel cell, Marcello? Could you guide us a bit through this? What kind of integration it entailed?
Yes, the system has been installed in Paris in Lab Prigen. That is a wide, let's say, infrastructure in Engie side in Paris. So they have an electrolyzer, they have a fuel cell, and the HyCARE system has been put in the middle. Actually, because of various trouble, some of the tests has been carried out with some hydrogen in tubes. Not all the hydrogen was coming from the electrolyzer. So just because of the testing, but the system is integrated. Of course, because it's a demonstration system, the flow of hydrogen from the electrolyzer and to a fuel cell is not yet fully optimized, because the system was mainly aiming to be demonstrated. But the connection from hydrogen produced from the electrolyzer about 30 bar and the hydrogen used by the fuel cell at about 2 bars have been demonstrated.
Okay, thank you very much. Very clear. Now moving on to HyStorIES, we have a question from the audience. You Arnaud, asking about the main parameters investigated to test the microbiological activity and whether these results can be extrapolated to larger periods.
Thank you for your question. So we have 4 parameters were selected, and they were selected because they are discriminant, and also they are measurable. There is no, for instance, the 4 parameters we have in this final risk assessment chart. They do not depend on the presence or not of a given microorganism or given family of microorganisms in the storage. They are criteria that are quite measurable, and they are water salinity, temperature, the availability of a carbon source, carbonate or dissolved CO2, and the availability of sulfates for sulfate reducing bacteria.
Okay, thank you very much, Arnaud. And I see there is also a question on HyUsPRe for you, Remco. Looking at the databases that we mentioned with the interactive information, and how they compare with the databases in HyStorIES. Do they complement each other in your view, or are they converging towards the same results in some cases? Could you tell us a little bit about this?
Sure, thanks for the question. Yes, I really believe that they do complement each other very nicely. HyStorIES took more a bottom-up approach to assessing the resource, the potential for storage in reservoirs that are not yet used for hydrogen storage or natural gas storage, for that matter. While we took a more top-down approach in HyUsPRe, where we looked at what is available for natural gas storage today and taking into account the location very proximal to transport infrastructure that might be reused for hydrogen as well. Natural gas transport infrastructure that might be used for hydrogen. So basically, on the one hand, the low-hanging fruit, so to say, the reuse potential of existing natural gas storage sites operating today versus the additional sites that might be developed in Europe, either onshore or offshore, in these clusters, which HyStorIES provided a perspective on in terms of potential capacities. So I believe this is a very complementary. The two data sets are very complementary. Yeah.
Good. Thank you very much for this. Yeah. I also have a question myself about I'm really not very knowledgeable at all, so it's going to be a very might be a silly question, but it's about the microbiological activity and how when you're trying to classify it at certain temperatures and pressures underground, will it always be similar across the sites, or is it going to be different even under the same conditions if we go to a different site? Because I imagine, like, for us human beings, our gut has different, bacterial activity, even though same temperature, same pressure. So it's kind of a silly question, but I don't know if you can provide some info on this.
It's shall I go first, Arnaud?
Yeah, sure.
Please go
Remco.
first.
Okay, that's fine. Thanks. No, it will differ per site. Yes, it very much depends on the microbial community that lives at the site, or that, and also on the parameters that Arnaud mentioned, right? So, but we're trying to. I think if you look at what research is ongoing in Europe, we're trying to, on the one hand, approach this more generically by identifying the key parameters that influence the growth of microbial communities or different strands of microbes, let's say it like that, whether they be metallogens, acetogens, or sulfate reducers, or so those are I think the three main groups, to be honest, if you discount iron oxidizers, so to say. And so we're trying to be generic about this. On the other hand, I also see initiatives that are more focused on site-specific study to better understand what the variability is across the sites in Europe. For instance, recently there was the HyLife project started under the CETP subsidy program, which aims to take a more site-specific approach and involves partners in operators with sites in actually providing sample formation waters and site samples for analysis. So, yeah, my perspective on it.
All right, thanks a lot. And then a quick question for you, Arnaud. You mentioned about you have in one of your deliverables where you rank the sites. You have the cost indicator, and then you have a suitability
Yes.
Suitability indicator, I believe. Could you talk to us a bit about this suitability indicator and how readers can interpret this?
We built, we call it technical suitability, and we built it to be complementary to what could be captured by the cost one. I mean, most of the suitability is reflected actually in the cost when a design can adapt to the conditions we can find, because in the subsurface world, we're not dealing with manufactured projects, manufactured products. Every project, every storage is different, and for instance, if we take like obvious parameters like the depth of the storage, it is actually reflected in the cost. So we did not include this parameter into the technical suitability mark that we set, even if we know that a site that would be is actually not suitable from a technical point of view, but it's from a techno-economic point of view, but it's captured by the cost. So we built this mark to integrate other information that are not captured, and it does include, for instance, the risks related to the microbiological activity that we just discussed. It does include, for instance, the nature of the cap rock, like salt, or would be better than some other rocks. It does include, for instance, the fact that there is or there is no abandoned well on this depleted field or on this aquifer. It does include the fact that there are some faults that are crossing the trap, and so elements like that are captured in this mark.
Okay, thanks a lot, Arnaud. We are already 10 minutes past our foreseen ending time, so I think we can close the session. Astrinos, we will have a question for you next year because you're still at the very early stages of your project. I hope it's okay.
I'm really looking forward to receiving it, and then I'll be in the position to provide efficient replies and tangible results. Yeah.
Great. Thank you very much to all our speakers for your great presentations and the nice answers you provided in the Q&A. And of course, to all our viewers online, thank you very much. And we'll be coming back at 2:30 with a session moderated by my colleague Lionel Boyot on pre-normative research. So stay tuned. Thanks a lot.